right, leading off where we talked about last time, we were talking about the energy levels. I just wanted to show you that the first energy level can have a maximum of 2 electrons. It doesn't always have 2, of course, because it depends on the number of protons. If it only had 1 proton, it would only have 1 electron. The second energy level has a maximum of 8, and again, it doesn't always have to have 8. But there is a possibility of 1s and 3p orbitals. And the third energy level has a maximum of 18 electrons, 1s orbital, 3p orbitals, and 5d orbitals. In biology, though, we only go up to the s and the p orbitals, or the end of the first line on the, the third line on the periodic table. Okay, the next thing we want to talk about is isotopes. Isotopes are varying forms of an element with different numbers of neutrons. So we're going to use hydrogen as an example. It's slightly confusing because we're going to have isotope 1, 2, and 3, but that is based on 1, 2, and 3 is based on this number that would be up here, or the atomic weight or mass of the isotope. So 1, 2, and 3 is not isotope 1, 2, and 3. It is isotope 1, 2, and 3, but it's based on the mass, not we're not just numbering them randomly. Okay, so this one up here, this is showing you, this is the atomic number. Remember that this is representing the number of protons, and this is the atomic mass number. This is 1.0079. As I was telling you before, this is the average of all of the naturally occurring isotopes of hydrogen. So what isotopes are forms that have varying numbers of neutrons. So in this case, let's say we have 3 of these. All of them would have 1 proton, right? Because if they had another number of protons, they wouldn't be hydrogen. So let's say if they had 2, they'd be helium or something like that. They also all in their pure form would have 1 electron. In other words, if they are non-reactive, they'd have 1 electron also. This would pack in the first energy level, right? Now the number of neutrons is the thing that varies. The first one would have 0 neutrons, the second one would have 1, and the third one would have 2. And that would make, because the atomic weight is the addition of protons plus neutrons, it would make the atomic weight 1 for hydrogen 1, hence the 1 that is up here in the left-hand corner, okay? Likewise, this one is 1 plus 1, or atomic weight of 2. So this is isotope number 2. This is 1 plus 2, or 3, isotope number 3, all right? The average is 1.0079, so which one exists the most in nature? That would be this one. That is one with 0 neutrons, 1 proton, 1 electron, and that goes back to the last lecture, how I was telling you there are no neutrons in that particular atom, all right? So those are isotopes. Now I'm guessing that there are 3 isotopes. Generally, or a lot of times there are 3. There's not always 3. So just to be simple, I'll kind of say that there's 3, even though there may not be. So we're going to use carbon as the next example. So carbon's average number is 12.011, and 6 is its atomic number. All right. So we're going to do carbon 12, 13, and 14. And what that means is the number of protons, of course, is always 6. Otherwise, it wouldn't be carbon. The number of electrons is also 6. The number of neutrons is the thing that varies in an isotope. So we're going to say that this one is 6, this one's 7, and this one is 8. That would make its atomic weight 12. That is C12. Okay? In this case, 6 plus 7 is 13. That would make this C13. Or 6 plus 8 is 14. This is C14. Okay? Now, C14, it turns out, is actually radioactive. It can give off particles. In this case, it would give off neutrons. And it would become eventually C12, but radioactive just means that it can give off particles. And because of that, we can use this as a marker. You can provide carbon to something that would be taking up carbon, and actually measure how much radioactivity is in certain parts of an organism. Let's say, for example, you gave carbon dioxide to a plant. It could take up that carbon dioxide and make sugars, and you could tell where that goes by looking at how radioactive certain parts of the plant are.